All right, so this is one proportional, the Z interval. Okay, so we've been talking about intervals, margin of freedoms, things like that. In inferential statistics, a sample is used to estimate a population parameter. So remember, the parameter is like what we're trying to figure out what we're going to get close to. And we're going to incorporate the margin of error into this estimate. So right now we are saying like we might have known a point of estimate with a margin of error that was like plus or minus a certain value above or below it. So they have a made-up fictitious person. It says, consider candidate Jones, who is running for the mayor of South Bend, Indiana. Anyone want to know it's in South Bend? Notre Dame. Notre Dame is in South Bend. Alligators. So the following excerpt from the news article about the election. It says, according to recent polling, candidate Jones currently has 54% support and has a margin of error plus or minus 4%. Okay, so it could go anywhere from 50 to 50 or 51 to 57. So you're counting the endpoints. The margin of error is a way of estimating the likely maximum minimum of the population parameter. In this case, the actual amount of support for Jones in the population. We include the margin of error of plus or minus 4 to the current estimate of 54, and we obtain 51.57. So right now they're saying that he has a 54% advantage, and they're saying it's plus or minus 4%. Okay, now this is where this kind of gets a little goofy. Notice they're saying it goes from 51 to 57%. Make that a little neater. Now this is what we have to do. If we had that 4%, we'd start at 54. We'd go 54, 55, 56, 57. Or if I was going down, I'd go 54, 53, 52, 51. That's how I'm getting the 4 points each way. Some people might say that it should go from 50 to 58, but you have to include the endpoint when you're counting. Okay, that's kind of goofy. The singular estimate of 54% is called the point of estimate. So that's the point of estimate of what he falls into the polls. The estimate is the single best estimate we have of the population parameter. In other words, if we had to name a single percentage as our best guess, the actual support candidate Jones enjoys, it would be 54%. The idea that candidate Jones is likely enjoying somewhere between 51 to 57% is called a interval estimate. So this is our interval estimate. And then we could also call that a confidence interval. Okay. The estimate is in many ways more powerful than the point of estimate. If candidate Jones wanted evidence that the level of support was over 50%, the interval estimate provides this. After all, the entire interval is greater than 50%. So this looks like this candidate Jones would win based on the margin of error. Okay, so the margin of error estimate population proportion is provided with the following formula. All right, I'll get that on there right now. So the MOE is Z star, or Z, I think that's supposed to be times, but they have P 1 minus P over N. Okay, that's the margin of error. Okay, so you might say, what is Z star? The variable is often referred to as the critical value. That is the number of standard deviations from the mean in both directions needed to capture the predetermined percentage of the bell curve. We already know a few critical values. We know the 68, 95, 99, 7 rule. If we wish to capture 68% of the bell curve, we need to move one standard deviation away from the mean in both directions. So the 68%, the Z star would be equal to 1. If we wanted 95%, that's 2 standard deviations, so your Z star would be 2. And then if you did the 99.7, your Z score would be 3. So this is where we're going to start doing some stuff. All right, so Z star is, we're going to use something called inverse norm. Oops. And then we call this halfway to 100. All right. So the halfway to 100 is a kind of a goofy idea, but it's simple once you realize how it happens. Okay, so if I had an 80% that I was trying to say that I was trying to capture, I'm 80% confident. If I wanted to say, what is halfway to 100 from 80, that would actually be 90. If I had, say, 95%, halfway to 100 would get us to 97.5. Okay, so those are things that we're going to go in and start taking a look at. So they have example 1. A random sample of 60 people shows that 75% support cutting property taxes. We wish to estimate the true percentage of all people who support cutting property taxes. And then it says find the margin of error of 90%. Okay, so they tell us 75% support cutting taxes. Not sure what's wrong with the other 25%, but we'll just go with this. And then they say we're going to create a margin of error of 90%. So what's halfway to 100? Yeah, it would be 95% or 0.95. Okay, so now I think, let's see how I'm going to do this. I think what we can do is we have to find the inverse norm. So what we have to do is when we jump onto our friend the Desmos family, I'm going to do where's it at? It's here, functions. I just have to see what it says. Visualizations, distribution. So we'll do the normal distribution, and we can easily do that from 0, 1, and then that gives us our normal distribution, which is fine. And then I'm going to go period, and then I can go back to functions and I find inverse norm. You have to do it this way in order for it to work. Just looking for it. So you got to make sure you have that period in there. And I'm losing it. Where is it at? Those tests. Is it inverse distribution? And then we're going to go a 0.95. Because that's the halfway to 100. Okay, so if we do that, we're going to come up with roughly 1.64. The big key on doing that is make sure you have the normal distribution with 0 and 1, unless they gave you a mean and a standard deviation, then you plug those in. But this, for the most part, is going to give us the value. So 1.64 is going to capture 90. If I go either way, if 1.64 to the right or 1.64 to the left of our mean, which we don't know, but if it was 0, we would capture 95% of our population, or 90% of our population would fall in there, where at either end I'd have 2.5% and 2.5%. Okay, so I'm going to go with 1.64. Let's go back here. So we're calling our z-score is 1.64. And so it'll be the 1.64 times the 0.75, because we're using this equation, p, 1 minus p over n. And then we're going to go times 0.25, because 1 minus 0.75. And then they said they use a random sample of 60 people. So divided by 60. So if we plug that all into Desmos, it should work out nicely for us. So I'm going to go 1.64. Oops. Wrong line. 1.64 times big old square root. I have a division in there. So I'm going to go 0.75 times 0.25 divided by our 60. And so I come up with 9.9. Why am I coming up with 9.1? Oh, he's off. Huh. So they came up with the 0.092, which I agree with. So that should be 9.2%. That's an error on his part. So the margin of error is 9.2 from the 75% of people. Okay, so 9.2 is what that would come out to. 2 places right to get you back to the percent, unless it's always given in decimals. So we are getting the margin of error at 9.2%. So we already know that we have 75% of the people that wanted to vote for this. And we're going to say plus or minus 9.2%. So that gives us 75 minus 9.2. So that's 4, that's 10, that's an 8, that's a 5, so 65.8% to, and then I'm going to add those together. So that's going to give me 0.29, that's 14. Carry the 1 to 84.2%. So that means that we are 90% confident that the interval between 65.8% to 84.2% are in support of cutting property taxes. Okay. And then example 2 says a random sample of 200 Cherry Creek students. What is conducted? 36 of the students plan to attend the next theater event. My phone is blowing up. What is going on? Oh, 9 messages all at once. I'm not sure how that happens. How did I get that popular? All right, so they say that 36 students are going to go to the theater. And then we wish to find the true percentage of students who plan to attend. So first off, I'm going to go 36 divided by 200, which comes out to 18%, or 0.18. And then we have to figure out our point of estimate. So find the margin of error of 99% confidence. All right, so what is halfway to 100 from 99%? 99.5. It's going to give me 99.5. percent. So as a true decimal, that's going to become 0.995. And then we can go ahead and plug this in to Desmos. It's a 0.995. Oops. 0.995, not 95. So that's going to give me roughly 2.6. So we're going to say that that gives us 2.6 if I do the inverse norm. Okay. And then once we plug that in, we're going to say that 2.6 and then 0.18, and then 1 minus 0.18 is 0.82. And then we had 200 people we were sampling. So we can easily find that on Desmos too, as long as I keep. So this is going to become 2.6 square root, divide, and we went 0.18 times 0.82 divided by 200, right? So we are 0.07. So now we are at plus or minus 0.07, which is 7%. So if we wanted to incorporate that with our 18%, we're going to go 18% plus or minus 7%, which that means between 11% and 7 plus that is going to give me 25%. And that's how we deal with the with that z value with the equation. So the big thing is the halfway to the 100. Think about the distance to 100, cut it in half, and that's what you'd be. So if you're at 80%, you're going to plug in 90% or 0.9. If you're at 70%, then you would plug in 0.15 because that would take us halfway to 100. Okay, so 5-7 is page 83 and 84. Or 5.8. Sorry, I'm on the wrong page. 5.8. So 85 to 86. And you can work on the rest of that. Cool. And then, so just so you're writing things down, let's see. So that's Monday, Tuesday, Wednesday. So we should plan on something as far as the test goes on Friday this week. Cool.